Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's presentation, Nature's Carbon Keepers, the planet-saving power of peat mosses, is brought to you by NatHab Expedition Leader Eleanor Edye. Eleanor earned her undergraduate degree from the University of Winnipeg with a dual major in biology and physical geography. She pursued graduate studies at the University of Alberta, researching tree-line dynamics in the Churchill region, which sparked her specialization in tundra ecosystems and bryology. Eleanor now works extensively in northern and prairie habitats as a NatHab expedition leader, combining her expertise in plant biology with her passion for Arctic and subarctic environments to guide travelers through these unique ecosystems. Eleanor, as always, we are so excited to have you here. The show is yours, my friend. Take it away.
Thanks so much, and welcome to everybody joining live, or if you're watching later, welcome to you as well. As Rob said, my name is Eleanor, and I am based out of Manitoba, Canada, so right in the center longitudinally of our big, beautiful country. And I work mainly for NatHab in Churchill as well as in Iceland, so lots of nice cold areas. I've been working with moss for over 20 years now. It was an accidental love affair, but I did fall into it when I was doing tree line dynamic work up in the Churchill region, and I was looking at what these trees were growing in. And as we'll be talking about, a lot of trees, especially in northern environments, a lot of the substrate up there is made up of mosses and lichens. So I spent better part of several years looking at mosses and fell in love with them along the way. So today we're going to be talking about moss, about peat mosses specifically, and kind of why they are so important, not just for like local habitats and trees, but actually for us and our entire planet. So depending on what your interactions with moss has been over the year, you might know it as something that you fight with on your lawn. Maybe you power rake it out. Maybe you buy a moss killer at the garden store. Maybe you buy peat moss to add to your garden as a soil enhancer. But I do want to take us on a journey and demonstrate to you in a shorter period of time than it took me to take over a few years that mosses are incredibly diverse. They are beautiful and important in their own rights, and they are also important to the planet. So I want to start with today talking about like what makes a moss, like how do you know that you're looking at a moss versus something else? What is peat and what is a peat moss, which is then a different subset of mosses? And then why this is also important. And while I know that some of you might need the end part, why it's important to stay engaged with why we're talking about mosses. You're coming along on this journey too, and so hopefully by the time we get to the subject of why they matter on a global scale, you'll appreciate even just a little bit more about how beautiful and interesting they are in their own right. I know it's a tall order I have set myself, because these are, for many of us, mosses are something that we fight against in our lawns. So let's take a step back and talk about what these actually are. When I was prepping for this webinar, I read a perspective about mosses that stuck with me, and it's that mosses are generally so small that we as humans are used to thinking of it as just a thing. It's a thing that grows on your lawn. It's a thing that grows on your roof or on your walkway. But every single part of that are individual plants. There are many species of mosses around the world, with over 20,000 species worldwide. Now, this might not be the heavy hitter that we see with, for example, flowering plants, which have around 300,000 species worldwide. But if we compare them with other groups of plants like ferns, there's twice as many mosses as there are ferns worldwide. There's 20 times more mosses than there are like gymnosperms and coniferous plants. So they do represent a large amount of biodiversity within the total plant group on Earth. Now, while I'll be speaking about moss generally and peat mosses specifically, it is important to know as well that they sit within what's called a bryophyte group. So with hornworts and liverworts, we often see these species kind of coexisting if you're in a garden center and you pick up a new plant and you look in the dirt, there's probably mosses and liverworts growing on that dirt, some of our common garden taxa. So they're often in the same places. They often grow intermingled. They are related, but they are not the same thing. But they're small, they're green. So people who work with mosses tend to also work with liverworts and hornworts. Mosses, as well as liverworts and hornworts, split off from the evolutionary lineage that led to all other land plants a very, very, very long time ago, close to 430 million years ago. So basically, as soon as green things got onto Earth, got onto the terrestrial part of Earth, mosses have been on their own separate lineage. Essentially, we had the development of stomata, which are they're a structure where we have basically a control of gas exchange between the cells of a plant and the overall environment. And then after stomata developed, everything went on their own way. So you can see stomata on the left-hand side there, showing you what they can look like. It's just a structure that the plant can open and close depending whether they want to be interacting with the outside atmosphere or just using the gas that is contained within their cellular network. So in short, they've been around a long time and they've been doing their own thing for a very long time. Overall, if you had to describe what a moss is, I would say they're overall pretty small. They are non-vascular, meaning that they don't have conductive tissue within their stems or within their leaves. They are non-flowering plants. And instead of spreading by seeds, they spread by spores or they spread by cloning themselves. Unlike your flowering plants like your apples or your roses or anything else that grows in your garden, or like all animals, they actually have a dominant haploid stage, meaning that when you see the green part of the plant, that part of the plant only has one set of chromosomes. When you see, like you can see on the right-hand side image here, a brown thing growing out the top, that is the sexually reproductive stage that's making the spores, and that is the diploid, or the stage that has two sets of chromosomes. Now this picture here is showing us the biggest self-supporting moss on the planet. Holy smokes. It grows up to, hold on to your hats here, 60 centimeters tall, or about 2 feet tall. In the moss world, that is gigantic. So it is a tropical species. It grows where there's lots of humidity, lots of forest floor to grow on. We don't see species this size really anywhere else, except in where they grow in water, where the support of the water can allow mosses to grow even taller. But if we're talking self-supporting mosses, Dawsonia here, Dawsonia superba, is the tallest moss in the world. Now, on top of kind of the other generalities we talked about, we often find mosses like growing on and in things. So they often mark a boundary between one thing and another. They might be growing on the forest floor, they might be growing on a log, they might be growing in a rock crevice, they might be growing on top of the rock. They do tend to live in sheltered areas, and the more shelter there is, the bigger they grow. But in non-sheltered areas, they can grow as well, and they can often be really, really tiny in those unsheltered areas. So this is one of the smallest mosses in the world, and I should say that there are lots of very tiny mosses. This is Ephemerum. This image here was taken in California, which, as you might know, is well known for being like either very dry or at least occasionally dry. So this is what's called an ephemeral moss, which means it appears when there's water on the soil and then disappears after that. So it just subsists within the soil as spores and doesn't grow until conditions are right. It is teeny tiny. So the plant as a whole is about 1 millimeter tall, meaning it's a little bit bigger than the edge of a pencil. Okay, so it's not the smallest moss in the world, but it is kind of on the same rough scale. Just to give you an idea, and even at this scale, we have the green part, that's the haploid stage, and the brown part in the middle is where the spores are being produced, and that is the sexual stage. So anything from like a cut soil bank that only gets rain once a year, it can have moss. Your roof can have moss. The Dawsonia growing in the forest is of course moss. Mosses have been around as long as we have had life on the terrestrial part of Earth. They have done well. Even if you don't spend a lot of time thinking about them, they're off living their own lives, unbothered. You might not see towering trees of moss, but there are mosses growing on basically every tree, right? There's mosses growing basically everywhere. They have had time to figure things out. So those are mosses in very brief summation. Let's talk peat. What is peat? The definition of peat changes a little bit depending on who you ask, but overall it is the surface layer of a soil that consists of partially decomposed organic matter, which mostly comes from plant material. So this image here is of an organic soil. You can see at the very bottom of the image that there's some clay underneath, and that's the parent, what we call it the parent material. So it's the part of the rock that's underneath all the soil. But what's growing on top of that is a lot of plant material and then partially decomposed plant material. This is what we call a soil profile. So we can look at the different layers of soil and they tell us a story. And we can see up at the top where it's labeled OF, this is fibric organic material, and it's where you can still see parts of the original plants, right? So it's started to break down, but you can still tell what was growing in it. And then as that peat formation continues and you see lower down, you get this very dark, rich, colored soil that has high levels of organic material, but you can't always differentiate what plants went into that anymore. These peat soils, they might be called a bog soil or a fen soil. They can also just be called muck. And it makes a very distinctive sound when you step in it wearing your rubber boots, and makes a very distinctive sound when you try to pull your rubber boot back out, mostly leaving your boots behind to fill in with water, and you find yourself in your socks. These types of soils don't occur everywhere in the world equally. They tend to be in very poorly drained areas, so areas where any standing water or any rainwater just can't leave. And obviously, as you might guess, they don't occur in deserts. They mostly occur in moderately to very humid areas. So like I said, the definitions of peat vary depending who you're asking and what the definition is for. But overall, this is kind of the look of a peat soil, right? It's very dark, it's very rich looking, it absorbs a lot of water, and it is light when it's dry, so not heavy. You might run into it in many places around the world, right? So where do you encounter peat in the wild if you're not walking through a bog? Well, you might encounter it in the wilds of your garden center. For example, if you search peat on Amazon, as I did the other day, you can buy bags of peat, like this one on the left, straight from Amazon, if not from your garden center. You can even buy peat blocks to burn in your fireplace. That one was labeled Irish peat for burning, in case you wanted to find it later. And then on the right-hand side there, peat's also used in things like smoking the hops for whiskey. No, sorry, so smoking the barley for whiskey production. So we do run into it in many places, but it is not made everywhere around the world equally. So I'm going to get you to hold on for a second because I am going to throw a few definitions at you and talk about what makes peat grow in different places. So I mentioned already that peat grows in depressions or in poorly drained areas where it's moderately or very humid. Okay, so sometimes we just call these places wetlands, right? You walk through, you get wet feet. Hey, it's a wetland. But do all wetlands make peat? The answer is no. A bunch of them make peat. We call these organic wetlands or peatlands. And of all of the wetlands that we have around the world, maybe about half of them will go on to make peat. And the other ones are what we call mineral wetlands. And these are things like just open water or marshes or swamps. But in terms of production of peat, we're looking for these organic wetlands that we call bogs or fens. Now, if you have somebody in your life who cares a lot about wetlands, this might be you, or it might be somebody else. You may already know the definitions of bogs and fens and why they're different. Those of us who got training in ecology and had to spend time learning about this at some point in our time have had at least one, if not more, very impassioned instructors try to shove these definitions into our brain of the differences between all these different types of wetlands. For today, we're just going to be talking bogs and fens. And the recipe for these bogs and fens includes a waterlogged site where we are oxygen deficient and possibly where we have acidic conditions as well. So both of these types of sites, our bogs and our fens, make peat. They have mosses that grow in them that contribute fully or nearly fully to that peat, but they are slightly different sites. The main difference between a bog and a fen is where they're getting their water from. So a raised bog, as you can see on the left there, the bulk or a large part of that bog sits above the water table. So it's raised above the surrounding area. It's getting its water from rainfall and from snowmelt. That means that it's not getting any extra nutrients that come in with that water. Raised bogs and bogs in general tend to be very nutrient poor because they're not being fed by groundwater, they're not having leaching from other minerals around, they're just getting what they can get from the air and from the rainwater. Fens are a different story. Fens are level or more or less level with the surrounding area. They might be lower than the surrounding area, and they are getting their water and therefore their nutrients as well, mainly from groundwater. So because we have very low nutrient levels in bogs and very high nutrient levels in fens comparatively, we tend to have a lot more species in fens than we do in the bogs. It doesn't necessarily make a difference for peat, but it does for biodiversity. So they are considered to be a spectrum. You can differentiate one from the other, but we go through from the spectrum from rich fen with lots of species. We have high nutrient availability, high pH, down to a poor fen where it starts to become more acidic, less nutrients, and then at some point it pops into the acidic side of things with low nutrients, and that is what we call a bog. Now that first image I showed, our landing slide there, that's a fen. That is a fen I spent a lot of time in when I was doing some bryophytes, some moss sampling there, and it's a very typical fen where you can see there's a little bit of elevation around the outside, so there's a lot of groundwater that seeps down. That particular site had very high calcium soils, so it was a very, very basic, very high pH. It had a ton of nutrients leaching through that soil and into the fen, and it was incredibly biodiverse. It was also very full of moss and very full of peat. Now, bogs, oops, there we go. Fens can look a little different as well, though. So fens can be very grassy. They can have some trees. They can have shrubs. But overall, we have a higher level of species richness in the fens typically than we do in the bogs. Bogs tend to have a real look to them, right? So they're not always very green. They often have some standing water around. They're often a little bit raised up around the surrounding area. And when you look at the water that comes out of a bog, it is like the color of a deep tea. So it's leaching a lot of tannins and other chemicals from the plants themselves into that water. As a bit of an aside here, when I was going through this webinar and kind of putting it together, I've done a lot of sampling in both fens and bogs over the years, and I thought to myself, I must have a lot of photos. I did not have a lot of photos for a couple of reasons. One is that when you're walking in a fen or a bog, your focus is on staying upright and not becoming one with the fen or one with the bog. So I was not really taking any photos. And then when I did take photos, they were almost always of carnivorous plants. So within the bogs, this is a very, very low nutrient condition. The plants that we have growing in there that are not mosses tend to be plants that are looking to get their nutrients from other sources. Bogs grow a lot of mosquitoes, they grow a lot of black flies, and these like flying insects are basically flying little bundles of nutrients to these plants. So things like Venus flytraps and sundews grow within bogs because they're trying to capture that nitrogen from the insects because they're not getting it from the ground around them. So just a little aside there. So let's talk about how we get there. So I got two soil profiles here. On the left-hand side, we have an organic peat soil. On the right-hand side, we have a regular forest soil. So you can see the difference in how dark the soil is and how thick the layer of soil is too. So forest soil on the right, you've got that dark band right at the top where the topsoil is being formed by the forest conditions. And it's, you know, maybe a few inches deep. That's the rooting zone for your plants. And then below that, you get into this, in this case, a lot of sandstone, some clay, and that's the extent of your soil, right? So your plants are mostly living in that top part of the soil because that's where the nutrients are found and that's where the roots are going to grow. On the left-hand side are our peat soil. This is basically like if you talk about what makes peat and how do you make it, at its base level, you get peat soil when you get more plant growth than you have decomposition happening. So we talked about how there's often prolonged like waterlogged conditions. It doesn't mean that it might not dry up seasonally, but mostly it's really wet, okay? So in that soil profile on the left, you can see that whoever dug that lucky profile was standing in water as they were digging it because that soil, or sorry, that soil pits is full of water at the bottom. So we have those waterlogged conditions. When we have those waterlogged conditions, it means that the soil itself loses the ability to hold on to oxygen. Now, the soil is never a high oxygen place, but there is oxygen that goes into the soil, like our little insects in the soil need oxygen, worms need oxygen, so all of those things that live within the soil need that. And the roots also need oxygen too. Where we have conditions that don't allow for oxygenation because all of those pore spaces in the soil are filled with water, it means that we now have these anoxic conditions and decomposition rates drop very, very low. So we simply do not have the bacteria, we don't have the insects, we don't have the fungi to break down that peat to become what we call like proper soil. So decomposition rates are low, production rates are high, and over time, that image that you can see on the left, you would expect about 1 millimeter, or about 1/8 of an inch higher every single year that peat is being produced at that site. So it's slow growing, but it is a growing thing. Peat bogs we generally find, I'll pull up a map in a second, but we tend to find them in areas that have been recently glaciated, not exclusively, but that's where a lot of our peat bogs are, and our other wetlands, because they left behind a lot of divots in the earth, and these divots fill in with water, and this water might not be able to drain. So how do you make a peat bog, or how do you make a fen? You're mostly taking a poorly drained site and adding a lot of time. So it might go from something that looks like this to filling in, filling in solely around the edges of that wetland. In this case, we still have nutrients coming in. They're being fed down the slope. This is still a fen type condition here. As time goes on, that wetland fills in with plant material and organic matter. This peat is now starting to grow. And over time, we can come to a point where we come back to this raised bog situation where the peat has now grown above the level of the surrounding area, and it's now being fed only by rainwater and snowmelt. And this gives us this raised peat bog, or a raised dome of peat. Now, I mentioned that this process takes a long time. We're talking since the last glaciation in most cases. So over 10,000 years, or a little bit less depending where we are, is how long it might take to build yourself a nice, mature peat bog. These are living things. They take a while to get there, and you can't really speed it up too much. Okay, so there's some peat, there's some moss. What is a peat moss? Put these two together, and peat mosses are just mosses that grow in these peat-rich areas. And as they grow, they don't decompose when they die. So they are adding that plant material to the peat every year. And like I said, around 1 millimeter per year is added to that. So to grow about 3 feet of peat, or about a meter of peat, that would take you, about 1,000 years to do that. Okay, so here's, I think, one of the really cool parts about peat mosses is that we talk about plants especially, and mosses even more so, like they're simply like existing in the environment. Like, oh, this moss grows on that tree. Like one thing had nothing to do with the other. Mosses, especially peat mosses, play a huge part in building this environment, not just in that they are growing in these spaces, but that they actually have characteristics that cause these spaces to exist. The moss makes these landscapes, so it's an ecosystem engineer just as much as, say, humans would be or a beaver would be, and they play a hugely outsized role in what their surrounding world looks like. So if you look at this here, the left-hand side is just a picture of a moss community, so a peat moss community. The red there is one of our species of peat moss. There's some grasses growing within here. There's some other species as well. It's not just one thing that grows in there. It is a whole plant community. And then if we take a sample of that, you can see on the right what that looks like as it continues to grow. So it's really just the top layer that is living and growing, and that all of those layers lower down are undecomposed plant material, where closer to the top, you can kind of tell what it was. Further down, it starts to break down more fully. So remember, mosses have had 400 plus million years to figure this out. They don't just love wet spaces, they keep the wet spaces wet. So if we have the question like, what came first, the bog or the plant that made the bog? Well, probably sphagnum has been around longer than we've had like anything like that we would consider a bog. Okay, so sphagnum is a type of peat moss. It's not the only one, but it is kind of the one that hits above its weight class, right? So there's only about 200 species of sphagnum worldwide. They're a very ancient lineage of mosses, and they were likely one of the first ones to split off from the other moss evolutionary lines. You can tell when a sphagnum is a sphagnum because it doesn't look like anything else. It is not similar to any other moss out there. Sphagnum mosses have a whole bunch of evolutionary traits that help those bogs become bogs and then stay bogs. They've got things like water retaining cells. They release tannins. They basically create a situation where there's so much water held within the area that everything is constantly waterlogged, stopping anything from growing there besides the sphagnum and the other plants that have been able to coexist with it. Everything about sphagnum wants to keep water close by. So if you look at the right-hand image here, you've got the growing tip there, the capitulum, and then you have branches. If you look at the branches, you have branches that kind of stand out from the side. Those are active in photosynthesis, so you can see that they're green. They got chlorophyll in them. They're collecting energy from the sun and converting it to sugar. But then if you look at the stem, you can see these long branches hanging down along the stem. These are what we call pendant branches, and they actually work to wick water up towards the top. So as that plant is growing upwards, even as that raised bog is getting taller and taller and taller, it's always going to stay wet because the whole plant is basically drawing the water up towards the top. When you look at the plant in like when it's magnified, it is pretty wild. Okay, so the leaves on this plant, let's go back and you can just see here, there's many, many leaves on each branch, but they're small. Okay, so they're maybe a few millimeters long, and they're only 1 cell thick. The leaves themselves have a network of cells where some of them are this dark green color here, and some of them are clear. So this is a network here of the live cells. The green cells are alive. All of the clear cells are actually dead, but they're at maturity, they're dead because this is what they're for. They are storage cells for water. And you can see here the pores within those cells are basically built to attract and then hold that water in just through capillary action. They're reinforced with those spiral thickenings so that when the plant dries, the whole thing doesn't collapse. But basically what that is doing is holding on to water to give the leaf its shape, to give the plant its shape, and ultimately to draw that water into the system and up into the top of the plant to keep everything else in the area away, because it's too waterlogged for basically almost every species of plant to live in it. Sphagnum is able to absorb about 30 times its weight in water. And of this plant, with those live leaves, only about 20% of the cells are alive, and the rest of it are these dead transparent cells that you can see. If you look at the stem, it has some similar adaptations. So the stem itself will also wick the water up. And you can see that surrounding the stem are these big, clear, open cells as well with big pores in them. Again, they've got those reinforced fibrils on them to hold the cells open so the whole thing doesn't collapse when it dries out. But then when it rains or when there is water present, it will retain and hold on to that water, drawing it further up the stem to the living part that needs it. And then just that image on the right there shows you the size difference between the living cells in the middle and the dead, those big spongy cells outside the living cell. So that's just a section of the leaf on the right there. So just kind of a wild adaptations here for such a small plant that most of us don't think about. And I know we're not at the why things matter part yet, but I want you just to imagine the sponginess of this plant. And if you had to pick one plant, you know, to mitigate runoff during a high rain event, to prevent flooding of your neighborhood, for example, how much work a single colony of sphagnum could do when it can absorb this much water and retain it for such a long time. And as it dries out, it releases it slowly, slowly, slowly. Now, I think sphagnum are incredibly beautiful. They, like I said, there's over 200 species worldwide. And even though they kind of have similar habitats, right, they all like to be wet. Some of them like to be more wet. Some of them like to be higher up and a bit more dry. Some of them prefer, you know, lower acidity or higher acidity environments. So in this image here on the right, you can see probably, looks to me like I see 4 species of sphagnum in that particular image. We have the red one that's quite beautiful, that's growing high and tall on this hummock. It would be a lot more dry up there. We have the green one around the side here. And then getting into the standing water would be another species again. And then kind of towards the back, there's a different species again that's living within a hummock, but not waterlogged. So some of these species of sphagnum, they're pretty floppy. They can only be in the water because they can't stand upright on their own. Some, as you can see with the red species there, have a real rigidity to them. The one that's likely in the water, that water, because we're talking about a raised bog, that pH might be as low as around 4, which is similar to a vinegar. And this is the condition that these plants have to grow in, is living within this acidic environment. So the combination of this acidity and some of the antiseptic properties of sphagnum is why this sphagnum, especially they call it the red sphagnum, was actually used quite often traditionally for things like diapering or menstrual pads. And also it was used as field dressings in the First World War because it reduced the amount of bacteria that would grow within a packed wound if you pack it full of sphagnum. So they've learned to live with these conditions, and not only have they learned to live with it, they create these conditions to exclude other plants from the area. Can't finish talking about sphagnum without talking about their spores. So this is what the spore capsule of a sphagnum looks like. Super cute. And if you go to a bog on a nice warm day and you sit and you are very, very quiet, you can sometimes actually hear the capsules popping open. They release explosively as they dry, and the spores will actually spray about 10 to 20 centimeters in the air, which is a lot for a moss, at an acceleration of 36,000 Gs, which is just a little bit below the acceleration of a rifle being shot. So I think that's pretty neat. Now, sphagnum is by far and away the most important group of peat moss that we have in the world in terms of actually making peat. But sphagnum are mostly present in bogs, and fens do make peat as well. Now, fen mosses usually do not have to work as hard to hold water. Remember I said that with a fen, your water table is kind of close to or at the surface. So they're not needing to pull up as much water to exclude other species. It's already waterlogged. They're already competing with other species because it's a very diverse area. But these mosses do have adaptations to hold and move water. So for example, here, this is Tomatitnum. And it's got this woolly, fuzzy brown mat along its stem, made of rhizoids, so like little root-like materials, and that is used as felt to draw the water upwards towards the growing tips and then protect it from any water loss as it dries up. We see other mosses through the fens as well. This is another beautiful one. This one is a Scorpidium. It's got these lovely channeled leaves. We call it one of our hook mosses. And again, those channeled leaves draw water upwards through capillary action. But as you can see from the image, most of the time, this moss is already in standing or moving water. So it's not having to go through, like, it hasn't had to adapt in the same way that sphagnum has to hold on to the water. But it's still there and it still makes peat. And this is not my picture, but I tell you, I've dug in a lot of fens and I can just hear this image because it makes a real glorp sound as you pull it out. And this is peat from a fen as opposed to peat from a bog. It is often a little bit more waterlogged. It holds a lot of water and it doesn't drain as well as the sphagnum peat does. But it is still peat and it is still retaining that organic matter within the soil. So all of this is really cool, I think. Hopefully you came along with me for why it's cool. Let's talk about why this matters. Okay, so here's a map of our global distribution of peatlands. Peatlands cover about 2% of our global surface. Now this map makes it look like a whole lot more than 2%, but please remember that peatlands are interspersed with other things. So when I look at peatlands up in Canada here, I know that there's a lot of peat, but it's interspersed with forest networks as well. So it's not covering that entire area. So peatlands about 2% of global surface area, but those peatlands hold about 20% of all of our terrestrial carbon. Carbon is important for climate reasons. This is a very simplified carbon cycle here, but it still helps us out. This is just the biotic side of the carbon cycle. We're not talking about volcanoes and rock formation. We're just talking about what's happening with the living things, okay? So we have carbon dioxide in the atmosphere. Carbon dioxide gets into the atmosphere a number of ways, right? It happens through us burning fossil fuels and through combustion. But also carbon dioxide comes out by respiration from animals. So we breathe in oxygen and breathe out carbon dioxide. Plants will also respire carbon dioxide. In many cases, it's less than what they're taking in through photosynthesis, but they do also respire. And in the ocean, both emits and absorbs carbon dioxide. As this carbon is cycling around within the atmosphere and within our biotic community, things like forests, for example, are known for storing a lot of carbon through like becoming a carbon sink. So something that's a carbon sink essentially means that it is taking in more carbon dioxide than it is putting out. A good example of this would be a forest. So if a forest is growing, we're starting from nothing, we're growing a forest, it is going to be taking in a lot of carbon dioxide from the atmosphere and emitting a lot of oxygen. However, forests age, trees eventually age and die, and all of that carbon will either be returned to the atmosphere through decomposition or will be eaten by other things and then again emitted to the atmosphere. So it cycles through. What's not going to cycle through is something like a peat bog. Once that carbon is taken out of the atmosphere by our little sphagnum moss doing its photosynthesis and laying down 1 millimeter of peat in a year, that peat's going to stay there until something happens to change it. So you're putting that carbon in a bog, and then until we change the situation, that carbon stays within the bog and it becomes a site of carbon sequestration. So carbon that is then removed from the atmosphere and not going back in. So back to this map here. We estimate worldwide that about 550 billion tons of carbon are stored in peatlands. And that is as much carbon as we have in all of our terrestrial biomass. So forests, humans, cows, everything living on this planet, we have as much carbon in all of that as we have in peatlands. And if we were to just talk about like plants, the peatlands have twice as much carbon as all the world's forests, even though, like I said, they only make up this tiny, tiny fraction of how much of our planet we have, 2% of our planet, and this outsized influence on how much carbon they are storing. So when we're talking about climate mitigation and how to protect our planet, conserving and protecting and remediating peatlands is often considered to be like a quote unquote, easy win in our climate change fight because they're already there. They're already doing this job and they're already like doing such a fantastic job of it too. Now, us humans, not necessarily doing such a good job of protecting the peatland though. So just if we were to zoom into some of North America here to give you an idea where things are in North America, these are soil maps, but the pink soils here are all organic soils. That shows you where some of the peatlands are. We have in Canada about a quarter of the world's peat, which I think is pretty amazing. And this here is actually a recent map from WWF Canada, using remote sensing to determine where the top terrestrial carbon storage is in Canada. So this is the darker the pink, the more carbon is stored in that system. So you can see all those dark pink areas up through like northern Canada and a swath across here. And then also in Western British Columbia are where we have a lot of carbon being stored. And then if I pull up just a different map here, just for comparison, the green map here is plant biomass. So this is things like forest, shrubs, grasses, roots. You can see where that carbon is being stored. I have to laugh, it's like not at all in the southern prairies, which makes sense. There's not a lot of forests down there. A lot of cows, some grass, but not that many forests. But when you look at what's stored in soils, therefore like our organic soils and peat, again, you can see this big swath up through kind of central Canada, just south of Hudson Bay here, and then into the Yukon and Northwest Territories is where we're finding these really outsized deposits of peat. Now, this project actually went so far as to divide Canada up into these 10-kilometer hexes and estimate peat storage in these areas. And if you zoom in and you kind of know the area, you can really understand that it's quite correct. For anybody who's been to Churchill, you'll recognize this right away. Clearly the Churchill coast. But it actually is. So we have this little black one here, and that's the Churchill River coming in, the Churchill River estuary. And if you remember, ever seeing any images of polar bears, you might think there's no peat out there, like all there is gravel. And that's indeed what we see along the coastline. There's a lot of gravel, not a lot of peat formation. But you go inland a little bit, oh boy, there is so much carbon being stored in these soils where it's darker here. So it's a pretty cool project with lots of great information. And just for comparison in the US here, outside Alaska, which is pretty similar to Canada in terms of how much carbon is stored in peat, there's not really much in the lower 48 going on. Northern Minnesota and kind of various areas here just south of Lake Superior have high levels of peat, and that's mostly about it, with another batch down here in southern Florida. So let's talk about ways in which we humans are currently not doing super great with peat and where we can improve. So in terms of the threats that peatlands are facing from humans, we have threats from harvesting peat, from draining peatlands, and from thawing and burning of peatlands. So when we're talking about peat harvesting, there's a few different reasons to harvest peat. In some countries, up until quite recently, peat has actually been used for power generation, as fuels for domestic heating. For example, in Ireland, a full phase out of energy peat is not planned until like this year, so they're still burning peat for energy production. Sweden, there's still peat used in some heating plants. Finland also uses peat in generation for electricity as well as wood fuels. It is considered to be a green fuel in that it is, you can grow it again, but you can't grow it within human lifetimes. Not even close, as we've said. So there's also peat harvesting that's for traditional uses, individual home heating, whiskey making. Those are not really the harvests that we're concerned about. And the biggest harvest of peat is actually for the horticulture industry. And I'm sad to say that this kind of harvesting happens in my neck of the woods. We have a lot of peatlands in central Canada. As we've talked about, in Canada as a whole, harvests around 12 million cubic meters. So that's like, let's say 12 million bales of sphagnum moss of horticultural peat every single year. Most of this goes to the US. And we supply 90% of North America's horticultural peat. Through operations like this, they basically come in with big harvesters, they skim off the top, 6 to 10 feet of this growth. They dry it, they bale it, they sell it. So this is a major loss point for peatlands. We've also historically and still currently drained a lot of peatlands. Now, I have to say, as somebody who lives in a rural area, there are still a lot of people out there who see a wetland and just start itching to drain it. It doesn't matter if it's a peat wetland or any wetland, but wetlands are often perceived as just like lost territory. You can't use it for your cows. You can't use it for anything, so you may as well drain it and do something with it. And in the European Union, drained peatlands are actually responsible for 5% of all of their greenhouse gas emissions. So I know like 5% is only 1/20th of that year, but that's 5% you could just take right off the top, right, if we stop draining peatlands. So Europe is the place that's lost more natural peatlands than anywhere else, having drained about 10% of its peat cover and lost that. In many cases, this was for things like forestry. It was for things like cultivation. Like this is a picture of a reforestation site in Finland. I remember taking a train through Finland many, many years ago and just seeing so many drainage channels. Everywhere I went, they were trying to drain the peatlands. And this was done just to boost the amount of wood that they could harvest, but in general, it didn't even get that job done. Now, anytime that we're draining peat, we're doing more than just draining these peatlands, right? If you reduce the amount of water in peatlands, you're reducing biodiversity. You are interfering with water storage, so that water table starts to drop, and your water filtration by native plants is likely reduced. You're increasing the amount of greenhouse gas emissions, and you're also increasing the risk of forest fires or peat fires in the area too. On top of that, the land itself starts to degrade. You have a functional peatland ecosystem that doesn't really want to be anything else. Now that you've drained it, it's just a dry peat, and dry peat burns pretty darn effectively. When we talk about carbon dioxide emissions from peatland, this is just from degradation here, so I'm just talking about drained peatlands. We see a lot of this in Alaska. Like I mentioned, we've seen a lot in Europe as well, but the biggest losses have actually been in the equatorial region, like around Indonesia. So we see this through a combination of deforestation and drainage, which is increasing rates of peat decomposition and the amount of fires in the area. And this is primarily done for things like, rice farming, sugarcane farming, as well as palm oil farming as well. However, there are easy ways back from that, and they involve restoring the water retentive capabilities of these peatlands. And there are companies and there are, nonprofits that go through and do this where anybody is willing. And peatland restoration basically involves, like, you take the ditch that you dug to drain your peat and you dam it so that it can fill back up with water. And sometimes you might need to come in and remove some of the trees that have grown up in the area since, and to help restore some of the original vegetation structure to the area. Once that restoration is done, you kind of have to keep protecting it for a while until it's a functioning peat ecosystem on its own again. But they can be rehabilitated, and they can be rehabilitated at low cost and relatively easily, as long as you're willing to let those systems be on their own. Now, some of the other issues that we're seeing around peat degradation have more to do with how we've changed the climate than to what we're doing directly. So thawing of frozen peat bogs is an issue that happens every year. So in peat bogs are peat bogs, but where there is permanently frozen ground, a lot of that carbon is stored within the frozen part. And if that frozen peat is really keeping that carbon locked away, if we have warming of the area, that can increase the amount of carbon loss and degrade that peat. It also sometimes dries it out. And where we see drying peat because of climate change, we also see an increased incidence of fire. And peat burns are, like, we know peat burns really well when it's dry. That's why humans have harvested it for so long for fire. We have this, if you've ever been affected by smoke from Canadian wildfires, you might be aware that a lot of the forest through this area burns annually. This is normal for this forest. It can be a lot or it can be a little, but within Canada, about 1% of the forest burns every year. But it's not just trees that are burning, it's also the peat that is contained within these sites. And where we see, reduced precipitation, so it might be lower snowpack, it might be less rain, higher winds, warmer air, that peat can dry out more than it has in the past and then contribute to the fire that's happening. And when peat catches on fire, it can burn a very, very long time because that surface fire can actually go underground. And those underground peat fires can burn for multiple years, reigniting later on, sometimes even into the winter, at a time that is not traditional fire season. So these are things that we can't directly address with the thawing of the permafrost and the burning of the peat without addressing our larger climate goals. But we can help address our larger climate goals by addressing keeping these beautiful, they're just gorgeous peat bogs and peat fens intact into the future. And I just wanted to finish us off here with this gorgeous photo. This is the Hudson Bay lowlands just south of Churchill, Manitoba. And I think it's a habitat worth protecting. And I think it's a habitat that is worth protecting, even if that means that we can't have as much sphagnum that we add to our garden every year. So if you think about keeping wetlands wet, we can keep these intact and keep our climate goals on track.
All right, Eleanor, thank you so much. All right, folks, before we dive into the questions, I would like to remind everyone that if you do have a question, feel free to submit them via the question fields in your control panel. All right, let's dive into them. Eleanor, do beavers help rehabilitate peatlands?
What a great question. And I was reading about this even just today because I've done a webinar on beavers. Go back and watch it if you want to. But the thing is about beavers is that we did such a good job as humans of basically eliminating them from the landscape that we are actually still learning how beavers and peatlands interact. There was a recent doctoral thesis published out of the University of Saskatchewan looking at peatlands and beavers, and it's one of the only studies that have actually happened now because we're just starting to get beavers back into the numbers where they can have a large-scale influence on these habitats again. And the short answer is, as many theses give us, like, we don't know, more information is required. But what we do know, even just from that initial study, is that they do have an effect. We're not quite sure fully what the effect is yet. That they do things like they dig up moss, they use sphagnum in their dams, and they have an impact on the function of the wetland, even when after the beaver's dead or it's moved away, the wetland is still changed by the fact that a beaver was there. And in terms of like how it affects the peat, or how it might affect a mineral wetland like a swamp, it's something that we are still figuring out. So I guess stay tuned on that one.
Gotcha, thank you. So what happens to the area from which the peat has been harvested?
Yes, so peat harvest, it does have a permanent impact on the harvesting sites. It is possible to rehabilitate a site like that, but it's not going to be rehabilitated back to being a wetland. We can get things like forest cover. We might have a forest plantation go in there. You might get something like an upland planted forest, but you're not going to have a wetland anymore. You've interfered too much with the hydrology of the drainage patterns of the area, and it's not going to return to being the same type of site, although it's not going to look like, a parking lot forever either. So there is remediation that's done. It's not done to the point of wetland recovery. So there are some new strategies happening now, not to the extent to address like all of the issues with peat harvesting, but doing things like collecting just the growing part of the sphagnum and leaving the peat intact. The sphagnum will recover. The sphagnum still has all the same properties that you're looking for in terms of water retention and soil amelioration, but then it can grow back. It's not done on a big scale because you're harvesting, the top 3 inches instead of the top 10 feet, but it is much more sustainable as an option if you still need that product for your soils or whatever else you might need it for.
So if it takes 1,000 years to grow 3 feet of peat, I mean, are we depleting the world's supply by buying it for our garden and heating our houses with it?
Yeah. Sorry, go ahead, Rob.
Yeah, what are the strategies for getting away from that besides, encouraging compost, and what is Ireland going to do?
Yeah, I mean, you've got it right. So we have a lot of other ways these days of generating electricity and generating heat, and it's just a matter of moving ourselves into the future a little bit faster, right? Whether it's hydroelectric, whether it's solar, whether it's wind, we don't need to burn things anymore to make electricity. It's we have technologically solved that problem, and then it's just the willingness to make that happen on a large scale. In terms of peat as a resource, peat as a resource is absolutely getting used up faster than we are making it right now. So how we address that in terms of, your gardening or the horticulture industry, it can be addressed by us individually by making choices about what we're using for our garden. Maybe you consider buying like a mix of wood chips and compost instead of adding sphagnum. If you do buy sphagnum, make sure it's one that has, a sustainability tag on it, that it was harvested in a sustainable fashion. And individual choices can make a big difference for this kind of thing. And it can make a really big difference too if we advocate with our garden centers to make sure that they are also making good choices where they're sourcing their products from as well. So it's not just what we're doing, but once more people start asking for different products, that's when different products tend to appear on the market. And we're not lacking other options, we're simply lacking other options in front of us right now. So the more we can ask for those other options to be made available, it makes it easier to make that choice for us individual consumers. For me, I did buy a bag of sphagnum maybe 10 years ago, and I'm still working through it. It has its places that it is, it's better than anything else. But you can ask yourself, is there anything else I could be using in place of this for this thing that I'm doing? If you're trying to grow Venus flytraps, you might still need sphagnum. There might not be anything else that does the job. If you're adding it to your garden, there's probably other things that are just as capable of doing that job besides sphagnum. And the best thing sphagnum can do for us is to keep staying in the ground, doing its job to sequester that carbon and keep it out of the atmosphere and to keep our lakes and rivers clear.
Is there any formal movement through policy or law that is helping to change this?
So I can speak most to Canada as well as to Europe, because we are the places that both have a lot of peat and still have a lot of intact peat. Worldwide, there are worldwide organizations dedicated towards the protection and better understanding of peat and peatlands. So yeah, there's actually a lot going on, and we do recognize that of all of our climate issues, this is an incredibly solvable one, right? We can do this. We can keep these plants in the ground. We keep them where they are, and they're going to do more for us there than they will anywhere else, right? The function of sphagnum in your garden versus the function of sphagnum in the ground, where it belongs, is so much greater in the ground where it's growing. So there's a lot of global effort being put into this. Some of it, rests on us as individual consumers to make better choices. Some policy changes are, they take a while to happen. But seeing things like Europe moving away from burning peat as a fuel source, that's not small at all, right? That's been decades in the making of moving all of Europe's power grid off of peat. That is not a small thing whatsoever. So those are some good news things that we can see. And then we also see, for example, within Canada, we recently had in my home province a big peat lease that was signed over to a First Nation. So it's going to be monitored, it's going to be, managed by the historical custodians of the land in a different way than it's been managed in the past. So some of those different types of ownership and different ways of looking at long-term use of a place are really valuable for questions like this as well.
Great. Well, Eleanor, thank you so much for your thoughtful answers. Unfortunately, it's going to be the last question that we do have time for today. So I'm going to hand it back to you for any closing comments you'd like to share with us.
Well, I would just like to thank everybody for being here today and for talking about peat loss with me. It's the thing that we don't think about that's probably the most important thing in your life that we just glance by every day and interact with the most without thinking about. So thanks for thinking about it for an hour with me, and I hope everybody has a great rest of your day.
Eleanor, thank you so much for joining us here today and opening our eyes to this. We really do appreciate the time you've given us. And I'd also like to thank everyone who joined us today. So if you are interested in information on how you can travel with NatHab, please give us a call at 800-543-8917, or you can send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us Monday for our next Daily Dose of Nature. You can check out next week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude today's webinar. So long, everybody. We'll see you next time.